Okay, today I would like to share an interesting topic for you. I think it's important. To me, it's important. One of the important thing I had to know as the robot engineering. So all the video I do here does share the experience, share what I know, what I learned, and my experience about robotic engineering from the college to now. I want to share all of you know about it. I'm not good at teaching or I'm not good at teaching, so I share what I know. Remember that. So um, I hope all of you understanding really the basic thing, and you can Google all the stuff I post on the YouTube right here is everywhere on the Wikipedia, a lot of the class online. But the thing is, I want to know is how understand that problem easily. When I college student, I try to figure out this stuff, and learning stuff is so difficult. And I want to learn experience from the other people, but I do not find anywhere. So some stuff is too difficult or some stuff is too hard, too simple. I mean, people don't share that. So I just want to do the video and share what's my experience and really detail some basic example. It help you clearly understand, and after that you can read more stuff and upgrade your knowledge later. So today I talk about common filter. Really, one of the important thing you had to know besides Monte Carlo localization, ROS, programming C++, and mapping, and the last thing, the path planning. That's all stuff the robot engineering had to know. To me, I had to know about all of them. That stuff. So today we talk about the common filter. This is a long project topic, so I will separate to several videos and talk about different things in the topic. In the common filter, we will have the standard common filter for linear motion, and another thing is the extends common filter for nonlinear and unstained common filter for highly non-linear motion, right? So what a common filter is, you can Google stop and searching the common filter. A lot of people talk about that. So I just summarize what I know about that. I used to read this stuff as a college student, but it's too hard for me at that level. I don't understand the math inside and what advantage, how to apply some real application. That's a question in my mind. I say, where is so, and how does stuff work on the real application? That's a question. Why do you need to know about this stuff, right? So year after year, I try to read again, watching another video. Okay, so far I see it's amazing methods for you, robot engineer, had to know about that, or control engineering had to know about this stuff. What the common filter is, so we have the lot of filter, in the electrical field, high pass filter or low pass filter, right? It's another filter help you get correctly the estimation, the variable. So, for example, but for the common filters, so you got only help you to get correct the estimation the data, okay? For example, right here you have a robot go to the water, the sea, to measure the pressure, but the pressure right here they fluctuate because the wave under the sea, so you get incorrect data, right? So how the common filter help you to get a estimate correct data right here is maybe the pressure, but in another application maybe the velocity, position, and temperature or something different, okay? Or in the computer vision, you can filter tracking. So this you a lot, but right here in this specific example, right here the pressure. So common filter will help you estimate the first time they estimate the pressure after the first measurement. They will update the measurement and they prediction another position, and they get the measurement update with uncertainty of the sensor. So they will give you the prediction. Okay, inside the robot they can create their belief, okay, and they compare with the sensor belief, so they give you estimate the value, right? It's really, I think it's really useful future to know for the robot too. They can give you exactly the location of the mobile robots where he is, okay. And in another example, in the 1960s, I think NASA we applied the computer to estimate the to get the trajectory estimation for the spacecraft around the moon. So and they also use this computer to have the spacecraft correctly get the correctly the estimation the trajectory around the moon. Okay, so and in this topic, I also mentioned for you about the fusion sensor. Fusion sensor mean you combine too many the data from another sensor. For example, right here, autonomous vehicle, they use the lidar data and radar data. So they combine to the data and they apply the common filter to get good estimation where the object, I mean right here maybe the pedestrian, another car, they can estimate correctly. And we talk about this one in the next video, another video, because there's the real application for fusion sensor. They track in the pedestrian people, okay, with the high dimension and non-linear motion. And right here, and they also use the right here the lidar sensor. They get the object detection, they get position, and they after the camera filter and to get the correct the tracking the object. And we talk this stuff later is more complicated, okay, but and the result right here maybe you can see the lidar data, they gave you this data and the real path, this one, the green one, but what the common filter results right here exactly it's really close to the real path, right? It's good result, but what happens if we increase in the noise environment or noise equipment or sensor? You know, they really incorrect right now. Yeah. So you can see how the noise and the uncertainty of the measurement, sensor measurement, impact to the common filter results. So that's one stuff I will talk later. Is we use this thing common filter or insane common filter. Okay, that's also. And so come back to the common filter. So what's common filter is, and they include two states, two really important. Okay, the measurement update and state prediction. Remember that in the common filter, they that two state measurement update and state prediction, and where they start in this loop. Okay, that's initial estimation. Okay, from initial estimation, maybe something really wrong and estimation, but after the measurement, and they will give you correctly the data quickly. So for the mobile robots, this really good application for the common filter, because mobile robots is the non-linear motion, so we had to use this method to get the correct localization of the mobile robot. Okay, so and before I go to the talk about the common future, so what do you think about uncertainty mobile robot and how they impact to the mobile robot? In the ideal world, for example, as robot move 10 meter, is exactly they move 10 meter, right? But the real world, you have so many things impact to the mobile robot. For example, the rock right here and the wet floor right here. They make the robot something slippery or friction, maybe slowly, okay? Um, and in the ideal world, they come to exactly 10 minutes, but 10 meters. But in the real world, they do not come to the 10 meter. They come to 9 or 8.9 meter because the environment, they make them move different location, or maybe the wind, they put the robot move forward 11 or 12 meter, right? So we can iterate this checking, testing 100 times. So what do you think? They give you the curve, the bell curve right here. People say the Gaussian, right? That's the Gaussian. They presented by the mu, the mean value, and covariant value. Covariant value is how uncertainty right here. The y right here. Okay. So and the y value right, the s value right here is the meter position, right? But the y value is mean the how often robot stop right here, this position, okay? And but in some environment, really good environment, for example, the factory, they don't have window or the floor is really good, and maybe the curve right here is narrow. I mean, okay, maybe some another environment, so a lot of the noise of environment is the big Y right here, as the covariance is really big. Okay, so what happened if they move after this one, after this first one, 10 meter continue 20 meter, 20 meter, the uncertainty will add up, stack up, okay? And location is really not correctly right so far, okay? For example, they move to 10 meter, 20 meter, the result is really different and the uncertainty increasing, this it's more uncertainty, right? So the robot will give you not give something wrong, right? Position. So the question right now, the robot need to something the method to get exactly the correct answer. Okay, so use the sensor. So sensor maybe in the ideal world, then so have the in ideal world they give the really good linear motion. It's linear data, really good data. But in the real world, they do not give you the good data. There's something up, down, fluctuate the data. So people call it the noise of equipment, the uncertainty of sensor measurement, right? So we had to use common filter to help to solve this problem. So before that, we had to Gaussian. I think people remember in the totem probability. So the Gaussian mean you had the present for two parameters. It means mu and its variant. The mean is more particle of current and lie in the center of the function, right? And the variant relate to the width of the curve, right? I think you remember the formula of the Gaussian. And total, the area under the curve, you remember total is equal to 1. So I think with this one, you can do something, the code in C++. It's really easy to calculate the Gaussian right here. You can use the formula and you calculate. Right here you get write the function mu, sigma, and double S. This is really basic. I go really fast to this one. It's easy to calculate. And okay, come back to the common filter. So the first one, the measurement update. In the measurement up, they have to stay, right? The measurement update and stay prediction. So we talk about the measurement update first. For example, the mobile robots, they have the prior belief with the mean and covariance right here, 20 the position of 20 meter, and the covariance about 9. And after the movement, after the measurement, the first measurement, the measurement right here, they show you the V is 30, is the mean 30, and covariance 3. So what the measurement update right here, it means you have to do the formula right here. This you create a new mean, a new variant. That's thinking. In the first time, you have prior belief, and after the measurement, you gain the knowledge about the where the robot is, and you know the new mean and new covariance. Okay, it means you get the more information, so the covariance maybe have to smaller, right? And you calculate the both areas right here, the new, the update measurement, and with the new mean and new covariance, right? Right here, let's use the formula I provide above, and you can guess the new mean and new covariance. You see, the covariance is smaller because we gain the knowledge about the where after the first measurement, right? So now robot he know where he is, right? And we can do some the small code in C++ about how to get that value. I think really basic. You already know. You look at it and you know it. And I don't want to talk so much about here. But I don't want to do this code. You remember we include a tuple. Tuple is something really have return to value at the same time. Right here. And you have to include a tuple, right? It's help you to in this code. That's plug into the formula, so you get return the new mean and new covariance. That's it. And I will attach the link how you read about the tuple on the tile right here to know a little bit about this in a C++. And okay, that's the measurement update. What about the state prediction? After we know the measurement update and we do the command ask the robot move to 7.5 meter with the new the motion, the uncertainty of the motion is 5, covariance 5. So what happened? So how the robot prediction last value prediction state right now? We use the formula right here. That's easy formula. You can plug mu1 and mu of the motion and covariance of the covariance of motion, right? You got the result. You can map this one based on the state prediction formula, and you can do the same thing in the C++. You can copy this one, go to the C++ and to do it. Okay, it's really easy. I don't want to talk so much right here. You can use tuple right here and write the new mean, new variable. It's easy and return you the value. That's the summary. The two important states phase for the common filter. Remember, measurement update and state prediction, right? With this formula. So in the high dimension, so I will show there's something different. The formula they show you two phase into the state vector, okay, in the matrix. But the for one dimension. So let's show you something really basic right here. For example, you have the for one dimension. Let us show you for one dimension to see how the command filter work. Okay, how they give you as really good estimation, right? For example, the measurement right here, you can measurement update right here. You can say prediction right here. You have the value from the measurement from the sensor. For example, your sensor measure from time t equals 0, 5, 1 equals 6, it's the time up, okay? And right here the motion, you ask robot moving 1, 2, 1 at t time equals 0, t time equals 1, t equals 3, okay? So how we get the estimate the value in this case? So look at the example the first time I told you in the picture. We common filters, we do this one again, sorry, this one again. So the first time where we start in this cycle is we start from the state prediction, but the first time we don't know where the robot is, we don't know, so we gave them the initial estimate. Maybe it's wrong, right? But after the several measurements, they converge the value, they get correct the value. Okay, so initial, for example, initial value right here, for example, this example, you can see initial estimate. Initial estimate, you got the mu about is the location of 35 meter and the significant density of 4. So after the first measurement, okay, the right now sensor at t equals 0, they measure the 5 meter, right? And how they update the measurement? Through the common filter, they will update the measurement right here. You can see they gave you the update measurement after the first measurement, right? Sensor measurement right here 5, and they update to 4.98, right? And covariance right here is smaller because they gain the knowledge, so they get the covariance 3.98. Okay, so we continue. After measurement update, they will predict. The robot will predict. Okay, where I stay in next movement. So for example, for next movement is 1, and the motion, the intensity of motion is 2. So use the formula, we add it up together. So for example, for 4.9, we add to 1 is the 5.98, and you have motion 2, you add 3.9, you got the 5.9. So robot prediction, okay, I got this location and the covariance in next movement. Okay, so in the next movement, robot's measure is 6. Okay, in next measurement is 6, and they continue update the measurement. Okay, 9 point. They compare the prediction and the measurement. Oh, they update the measurement. They got the result right here, and covariance right here. And they continue. They move. They predict the motion. They move to 1. Okay, and the motion is 2. Okay, they plus 2. With the 2.39, they get 4.9 covariance, and prediction they plus, okay, 5.992, the plus 1, because the prediction our robot will predict this net time, next location, this position covariance. Okay, and in next location, they measure the sensor measurement is 7. Okay, they continue. they continue, compare, and update the measurement between the prediction and measurement. They gave you the new value. Gave you the new value, okay, right here, and they continue prediction. Okay, right now they ask the robot move 2 and move the uncertainty is 2, so they got another prediction of the robot. But when the robot move to 9, okay, they correct this value and they update the value measurement right here. And they continue move to 1. They predict and predicted state, okay, right here, this value, and they move to the measurement is next measurement is 10. They correct, they update the measurement 9.99 and covariant 2, okay, and the last one they move to 1. So you got this prediction of the next state, the last state right here, 10.9999. okay, really good prediction, right? So go to how to program. I want you to program this one to get a result to see between the update measurement and prediction state of the robot. You can use the Visual Studio and download it from the Visual Studio 2019. It's really good environment. And in some next video, you can see I use the eigenvector because eigen really good for you the matrix or linear algebra. So libraries you have to add it up. Your library, how to add it is easy. You can go to property right here and go to C and you add your library. You download library and you add the library into this one. And in your code, you say include eigens, so you can use the eigenvector. In this example, because this is state vector, so I want to show